All right. So let's finish our discussion of alcohols this lecture period here. We're going to pick up where we left off last time, which was tertiary alcohols. We had to put them in a different category than our primary and secondary alcohols because they undergo a different mechanism that has this carbocation intermediate, what we call an SN1 mechanism. This is where your leaving group just kind of falls right off, leaving you with this carbocation intermediate, and that's what ends up getting attacked by your nucleophile. Okay? So when we convert to a good leaving group, we have these two strategies, either to convert to an alkyl halide or to this tosyl chloride. All right? This one was new, but this really wasn't any different than primary and secondary alcohols. All right? Remember though, for primary and secondary alcohols, in order to convert to one of those alkyl halides, we had to use these fancy reagents, either our thionyl chloride or our potassium tribromide. When we're talking about our tertiary alcohols, all of a sudden we get to use this way cheaper, way easier method of just adding either hydrochloric or hydrobromic acid. All right, so what gives? Why can we just do this method instead of using our method that we used for primary and secondary? All right, so we're going to see we got one other method of replacing our hydroxyl group here with a better leaving group. All right, and that is to protonate it under acidic conditions. Okay, by taking that hydroxyl group and adding a proton to it, then when it leaves as a leaving group, it doesn't leave as that strong base hydroxide, it simply leaves as a neutral water molecule. Okay, so one more strategy to get rid of that OH group is going to be to protonate that OH group. Okay, so let's do our mechanism here. We're going to take this tertiary alcohol, with its two lone pairs. We're going to take a strong acid like hydrochloric acid. All right, and as I said, what we're going to do is protonate that alcohol. Right, so now it's going to have this extra proton on there, meaning it has one lone pair and a positive charge. I need you to fill in our missing electron pushing arrows. Take me from A to B here. Okay, so I have this new bond between my oxygen and my hydrogen. Where did that pair of electrons come from? Was that lone pair on that oxygen atom is going to reach out and grab that proton. Okay, I got to then break my HCl bond, leaving me with that chloride ion. Okay. So the next step in our mechanism now, because we have this tertiary carbon, it will efficiently form that carbocation by kicking off that leaving group. So everybody take a second and draw me my intermediate here. Follow my electron pushing arrows. so we can note our inorganic water molecule has been displaced here, leaving us with this carbocation intermediate. That carbocation intermediate is going to react with that chloride ion from our first step. So everybody take a second, see if you can't finish off this mechanism for me. Fill in the missing electron pushing arrows, and then finally the product of our reaction here. That chloride ion is our nucleophile. It's going to attack that electrophilic carbocation. So that's how I get my substitution product. Okay, and I can turn around and I can take this and then efficiently do a substitution reaction with one of our nucleophiles. We had mentioned last class, and now let's show it, about the stereochemistry. Because of this carbocation intermediate, we have different stereochemical implications than we did for our previous reactions. So let's say stereochemistry of this SN1 mechanism. All right, well, let's start out with a stereospecific alcohol here. Try to make it smaller. We're going to give this molecule a stereocenter with that alcohol group. Still going to make it tertiary. All right, let's show what's going to happen here by doing our mechanism. We have our hydrobromic acid. All right, see if you can't remember that very first step. What's going to happen first? Protonate that hydroxyl group. Right, because this is tertiary, that good leaving group will leave. And this is kind of the important part here. Before that leaving group leaves, we have a chiral carbon because it's got 4 distinct bonds and it's got this tetrahedral geometry. Well, when that leaving group leaves and we form our carbocation, carbocations have only 3 bonds and will adopt this trigonal planar geometry. Right, so whereas here my chiral center was a tetrahedral, over here this is a trigonal planar. And as the name implies, that means that it is flat. right? A plane. So when I take my incoming nucleophile, my bromide ion, that bromide ion can either attack from the front side or from around the back side, and you're going to get a 50-50 mixture of both. All right, so we're going to get what we call a racemic mixture, a 50-50 mixture of all possible, of our two possible stereoisomers. All right, so either I could draw my products as a mixture of both, one where the bromine is on the wedge, and the other one where the bromine is on the dash, or we can get lazy and just use our straight line bonds. Right? If instead I just said this and this, all right, these straight line bonds, we know this is a stereocenter because it's got these four distinct bonds, but we haven't indicated a specific stereochemistry because we're not using our dashes and wedges. So this is how we can easily represent this racemic mixture. So even if we start out with a stereospecific alcohol, we will lose that stereochemistry when we do our SN1 mechanism. Or rather, we'll have an equal distribution of both. Okay, so then just to finish this off, because we are then going to take this and do a substitution reaction, I'm going to start out with this stereospecific alcohol. All right, I want to know what happens when first I treat it with HBr, and then secondly, we're going to follow it up with some nucleophile. And let's use one of our weak nucleophiles, one of our neutral nucleophiles, so we can make a point here. All right, so after that very first step, we've already lost our stereochemistry when we formed that alkyl halide. We don't have to draw our dash wedge bonds. We're just going to draw it as straight line bonds, indicating that racemic mixture. Okay. Now, the one thing that we do got to note is our neutral nucleophiles. Let's just do our mechanism here to prove a point. Remember, these tertiary alcohols, that good leaving group is just going to fall right off, is going to leave, leaving us with this carbocation. And now let's take, since we got such a strong electrophile here, we can use that neutral nucleophile to attack. All right, but what's my intermediate, what's going to be right here after I attach that neutral nucleophile? Everybody take a second. Draw me the product of this step in our mechanism. What am I missing on this intermediate? The charge, right? So my nitrogen, now it has 4 bonds and no lone pairs, so it should have a formal charge of +1. Okay? So these neutral nucleophiles, when they attach, they will necessarily have this positive charge. They're not going to stay like that. Our neutral nucleophiles will always lose a hydrogen. All right, so if we want to finish off our mechanism here, we have this nitrogen. Now it's got 4 bonds. So it's got this positive charge associated with it. Well, there's going to be some base that comes along and retrieves that nitrogen. We're just going to do generic base here. You could use the bromide ion, although bromides are crappy bases. It does give you a balanced chemical equation, but typically it's actually the solvent that's going to be accepting that proton, not actually the bromide. So we're just going to use B for base and show that that accepts that proton, leaving us with our neutral product. So let's just make a note. Anytime we're going to use a neutral nucleophile, you will note that all of our neutral nucleophiles that we listed, they all have a hydrogen on that nucleophilic center, and that's because they'll lose that hydrogen throughout the course of that nucleophilic attack. Cool. All right, so we got our substitution of our tertiary alcohols, first converting it into an alkyl halide. When that happens, we're going to lose our stereochemistry. It's going to go through yet another SN1 mechanism, forming that carbocation intermediate, when we then react it with some nucleophile here. All right, we got one more class of reactions to go here. Our elimination. Of our alcohols. Or even more specifically, because this falls into this general class of reactions called elimination reactions, specifically because we're talking about alcohols, we could also call these dehydration reactions. And that is because we're going to see our alcohols lose that hydroxyl group as well as another hydrogen, so they lose the equivalent of a water molecule. All right, so let's just take a look at a very simple example here. We're going to take a look at the Lewis structure of ethanol. Again, if we do a dehydration reaction, we're going to lose a hydrogen and an OH, an equivalent of a water molecule, and we're going to form a carbon-carbon double bond. Now, I know what you're thinking. Everybody's like, wait a minute. At the very beginning of this chapter, we learned how to go the exact opposite direction, what we called hydration reactions. So what gives? Which way is it supposed to go here? Okay, so it depends on what set of reagents you use, although they are going to look very similar. For hydration reactions, we use dilute H2SO4. Or we would write that H2SO4 and water. If we're doing a dehydration reaction, we use very concentrated H2SO4. And the real key here is the other component, heat. Okay? So let's rewind back to Chem 1B for a second and remind ourselves about how thermodynamics works. We have our delta G, which tells us whether or not a reaction actually occurs, right? Whether or not a process is favorable under a given set of conditions. And it's got these two components to it, the enthalpy and the entropy. Okay, so it turns out that one of these processes are favorable from an enthalpy standpoint, and that is our hydration reaction. All right, this is delta H favorable, meaning that the energy that it takes to break that carbon-carbon double bond is less than the energy that's released when you make these new carbon-hydrogen and carbon-oxygen bonds, right? So from a bond making and breaking standpoint, this hydration reaction is the one that's more favorable. But as we learned in Chem 1B, this term right here becomes more and more and more important as you increase the temperature of that system, right? As we crank up the temperature, the entropy component becomes more favorable. And it turns out that breaking this molecule up into these two smaller components is an entropically favorable process. So at high temperatures, we have this entropically favorable dehydration. Okay, so we can kind of tune this equilibrium to go in one direction or the other by using temperature. At low temperatures, the enthalpy term is going to dominate our free energy. At high temperatures, the entropy term is going to dominate our free energy. All right? We talked about going this direction at the beginning of the week. Now we're talking about going this direction, our dehydration reactions. Cool. All right, so okay, our dehydration mechanism here. We're going to see something similar to what we just saw in our previous reaction mechanism. We're going to convert that hydroxyl group to a good leaving group by protonating it. Okay. So some textbooks distinguish between our mechanism for primary and secondary versus tertiary. But I'm going to tell you, I've done these reactions a ton in the lab, and they're full of shit. The bottom line is primary, secondary, and tertiary all undergo what are called E1 mechanisms, meaning we have a carbocation intermediate. For those primary alcohols, you do have to crank up the temperature quite a bit more, but the bottom line is when you put enough heat into these things, that leaving group will fall off, giving you a carbocation intermediate. All right, now, when we have our carbocation intermediate, we have to worry about these hydride and methyl shifts, but that is going to complicate things way too freaking much for our purposes. So I'm going to lie to y'all a little bit, and we're just going to take it as a simplifying factor because otherwise things are just absolutely insane. We're going to say we're not going to worry about shifts. I will tell you in the lab, and I think it's pretty cool, you get maximal shiftage. I mean, you get every freaking possible alkene that you could possibly dream of out of these molecules. But again, that's just going to be a little bit too much to keep track of here. So we're going to just say no shifts that we're going to be worried about, despite these carbocation intermediates. Okay, so then let's do one of our mechanisms here. All right, we have this strong acid and heat. And like I said, that very first step is going to be this common strategy we have for getting rid of that hydroxyl group. We're going to protonate it. All right, so see if you can't fill in that first step in our mechanism. All right, let's protonate. That lone pair on that oxygen is going to reach out and grab that hydrogen. Okay, like we said, we're going to form that carbocation intermediate, so let's kick off that good leaving group. Take a second and draw me my intermediate. Okay, let's just note here, important to count carbons, 1, 2, 3, 4 carbons. So that's how many I should have in my intermediate as well. All right, but then here's the tricky part. How do I get to my product, my dehydration product, right? First of all, what's the functional group of our dehydration product? Alkene, right? So we should always get an alkene at the end of this. How did I get my alkene here? All right. So importantly, let's look at these two and let's fill in our implied hydrogens. All right, these first two are the same. How many hydrogens do I have on this carbon up in my product? Just one. And what about down here? I have 2. All right, and then there's 2 up here. My carbocation only has 2. All right, so the big difference here is the number of hydrogens on that second carbon. So let me get rid of all these for the sake of not having too much going on. Oops. All right, here we have 1 hydrogen. Here we have these 2. All right, and so importantly, it's going to be this lone pair, or I'm sorry, not lone pair, this bonding pair of electrons that becomes my new carbon-carbon pi bond. All right, this pair of electrons is going to come down and form a new bond with my carbocation. All right, we have to have some base, and since we just produced water, water's a decent base under these acidic conditions. All right, so let's go ahead and make water our base. All right, we gotta have something to accept that hydrogen. It's not just gonna go flying off into space, and that base under acidic conditions will use water. All right, so importantly, if we just want to keep track of what carbon's what in our reactant here, yes, that red carbon loses that leaving group, but its next door neighbor is also involved in this reaction, right? Its next door neighbor is what ends up losing that hydrogen to form our new carbon-carbon pi bond. Cool. All right, so let's do another one here. We're going to hit this thing with our concentrated H2SO4 and heat. All right, I'm going to tell you there's more than one product for this particular substrate here. So see if you can't give me our more than one product for our dehydration reaction. All right, so why do I have more than one product? So again, our leaving group is definitely going to be kicked off here. So that carbon's going to be involved in my double bond, my carbon-carbon double bond. But now I got these two different neighbors. I have this one over here and this one over here. All right, if my blue carbon loses its hydrogen, that would leave me with this alkene product. And if instead it's my green one that loses its hydrogen, that would leave me with this alkene product. Right, so I have two neighbors, and since that neighboring carbon is also involved in this reaction, we're going to get a mixture of both of these. However, one of these is going to be present in larger quantities than the other one. All right, which one of these would be my major product and which one would be my minor product? All right, let's take a guess here. Who thinks the one on the left is going to be the major product? And who thinks the one on the right is going to be the major product? Why the one on the left? More substituted, right? So this one's more substituted, more stable. Okay? All right, now, there's actually a third product as well. Awesome, okay, cool. So, what is our third product? This one's very hard to see because if we look over here, we can see how we got this alkene. We just erased this and put a double bond here. And then for the other one, we said, all right, I'm going to erase this and put a double bond here, right? Check, check. That's how we got our two products. However, this molecule is not frozen in space, right? It's not just floating around in solution with all of its bonds super rigid like this. It is rotating about all of those single bonds. And so this bond right here can rotate. And so yes, this is one way to draw the conformation of that alcohol. But this right here is the exact same alcohol. Right? It's not a different stereoisomer because we can rotate about our single bonds. But if we draw it like this, it can be a little bit easier to see how we get a third product here, which is exactly our Z stereoisomer. Yeah. Oops, not that one. All right, we don't have any stereoisomers of this first one because it's a terminal alkene, but these internal alkenes, we have both the E and the Z conformation that's going to be produced. And out of that E and Z conformation, which one would we expect to get more of? What's going to be in a greater abundance in our reaction mixture here? E, right? So now this one's got our favorable stereochem. So again, more stable. This one's got our unfavorable stereochem. So it's less stable. Okay, so our major product in this reaction mixture will be our more substituted, more favorable stereochemistry product. The other two you'll actually get a mixture of all three of them. It's pretty cool. You see all of them in solution, but you will see majority of your E molecule, or plurality. Most of it, the major product will be that E. Okay, cool. So the bottom line is we got to worry about how many neighbors that leaving group has. That's our first consideration. But we also got to make sure that we don't have different stereoisomers of our alkene. So let's do another one here. I'm going to put two more down. All right, I want you to draw me all possible products and then label the major product. Say it again? That's more or less what we call our degree of substitution here, right? So I honestly don't remember which term applies to which, but Zaitsev is the less substituted one and Hoffman's the more substituted one, or is it reverse? Okay, so the bottom line is, yeah, we just kind of boiled that down to degree of substitution, right? And you will get a mix. Importantly, it's not directed at one way or the other. You will get a mixture of both of them. It's just you'll get like 70% this and 10% this and 20% this, right? So you'll always get all of them in there. Whichever one is present in your major amounts is going to be what's the most stable. And there's these two factors you have to look at: degree of substitution and the stereochemistry in order to decide what your major is. All right, let's do this first one together real quick. Make sure that we sort of got the basics down here. I look at my leaving group, that hydroxyl group. It's got two neighbors. So either one could be involved in this chemical reaction. If it's the green one, that would lead me to this product here. And if it's the blue one, that would lead me to this product here. All right. In this case, I don't have any other stereoisomers because these double bonds are locked in this ring, so I can't flip any of those carbons, any of those groups around. So I got to determine which one's going to be my major and which one's my minor product. What do we think, left or right? Right, so the more substituted, this one's a tri-substituted, this one's only a di-substituted, so indeed this will be my major product. All right, so I'm going to play the same game with this one. I'm going to say, all right, I know that my carbon with my hydroxyl group. We got to get rid of that hydroxyl group, but also a neighbor is going to be involved in this reaction. So if it's these two here, that would lead me to this product. And if it's these two here, that would lead me to this product. All right, but then we got to ask ourselves, do we have any stereoisomers of these two products here? All right, first of all, does this one have any stereoisomers? No, how can I tell? Remember, you got to look on either side and see if any of them have, let me move it over here just for some room. If either of those two carbons are bound to two identical groups, as is the case here, there are two hydrogens on this side. That means there's no stereochemistry in that bond. This is the only possible alkene I can draw between those two carbons. But what about this one over here? This one does. This would be the E conformation. In order to draw the Z conformation, you're going to pick either one of these two carbons. And it doesn't matter which one, but you need to flip the groups. Right? So you could pick this red carbon and instead draw the methyl group pointed up. That's perfectly fine. Or you could pick this carbon right here, the green carbon, and swap your methyl and your ethyl group. Either would give you the exact same molecule. All right, so because that methyl group is smaller and easier for me to move, I'm going to do that. I'm just going to draw it pointed up. If you did it the other way, then your molecule on your paper would just be upside down compared to this one here. All right, and which one of these is more stable, the E or the Z? The E, right? Because we want these big groups. This big ethyl group does not want to be crammed next to this methyl group. We'd rather have these two small groups next to one another. So this is our major product. Cool. All right, awesome. We will dive into our next chapter on epoxides next class. Yeah. This one here?
Yeah, I'm struggling on my...
Yeah, because when you cut this double bond right here, this is low and this is high on this side, and this is high and this is low on this side. So they're not on Z-Zame Zi, the two high groups, which is why it's the E conformation, right? If your high groups are on opposite sides, it's E. If they're on the same side, it's E. Yep.
Thank you.
Yeah, have a good one.